So I owe you the proof outstanding from yesterday. So you remember the theorem that we formulated and started discussing. So assume that 1 over h squared EH, the infimum over W12 deformations, 1 over h squared EH converges to 0, actually, when h goes to 0. Then first condition, first assertion was that minimum of I2 equal to 0. That was a trivial outcome from knowing that 1 over h squared EH actually converges, gamma converges to I2, and which is equivalent, and that was a non-trivial observation, to which is equivalent to the vanishing of certain 3 Riemann curvature components on the mid plate. So R1212 was equal to R1213 equal to R1223 at x prime 0, equivalently equal to 0 in omega, that is the mid plate. Right? So in particular, that condition is in fact equivalent to EH, infima of EH scaling faster than h squared. And then statement 2 was that the kernel of I2, because I know that it minimizes to 0, consisted of rigid motions of just one isometric immersion. And so this is Ry0 plus B over all R's in SO3 and B in R3, where Y0 is a uniquely defined smooth, it must be smooth, not just W22, right? Uniquely defined and smooth isometric immersion of G, that's our Prestressed metric, restricted to the mid plate and just 2x2 component. Okay, so we discussed the proof of 1 and 2, and now I want to show you how I get 3. Namely, 3 is that automatically then infimum of EH must scale at least like h to the power 4, right? So we discussed this extensively. There is this another energetical barrier, right? So in the first and the second class, we've seen energetical barrier that is the jump to, to something non-positive, not even in the context of non-Euclidean plates, but in the context of general bulk non-Euclidean elastic materials. So here is another energy jump from h squared, right, to immediately h to the power 4. So to prove that, just recall, so now we will see the proof, the sketch of proof of 3, because that's useful for other jumps in the energy that we will formulate, but not prove later today. But before doing so, let me remind you what was I2. I2 of y, so I2 was defined on y's, such that gradient y transpose gradient y equals to that g of x prime 0, 2 by 2. Y has to be W22 from omega to R3. And then I2 is defined only on such y's, otherwise it's plus infinity. So I2 of such y is, I don't want to write constants, so this is like integral on omega. And again, just morally speaking, although we have a very precise formula, here I get the measure of what? Of gradient y transpose gradient b, symmetric, part of it minus 1/2 B3 G X prime 0, 2 by 2 squared X. Now what is this B? So when I have an isometric immersion Y of this, then I can compute B by means of the formula D1Y, D2Y, and B. Okay, so I call this matrix capital B. And then the requirement is that B transpose B equals the full metric G, not just the 2 by 2 component of it. So G at X prime 0 all the time on the mid plate. This is only defined on X prime, the mid plate variables, and the determinant of B positive. Okay, so once again, what is happening when I have, in particular, a minimizer of, so now I want to prove 3, so I know that I2 minimizes to 0. I've already checked that up to rigid motions, that minimizer is unique. It's a smooth Y0, and that Y0 has its own B, okay? Defined uniquely defined by this formula. And I know that I2 of this Y0, which, okay, not just W22, it's smooth, but satisfies this isometry condition, equals to 0. So let's see what we can get out of there. So clearly, infimum of EH is bounded by EH of UH, where my particular UH that I want to discuss is defined by means of Kirchhoff-Lab ansatz, although it's augmented, as we will see, out of this minimizing immersion. So UH of X prime X3 is Y0 of X prime, that's my Y0 here, plus X3, B1. B1 is the B corresponding to Y0, okay? So if this is Y0, then I call B1, because I will have another generation of Bs. Plus X3 B1 of X prime. And then I have X3 squared divided by 2. I will have a certain B2 of X prime, and this is to be defined. Okay, I tell you what it is. So this is given, and that's how I define my UH. So then, right, I want to compute EH, which is integral 1 over H, integral of omega H, what? W of what? Of W evaluated on gradient UH times G inverse 1/2. So I have to compute what that is. So, what's the gradient of UH? Okay, so let's collect the terms in order of powers of X3. Where I don't have power of X3, I have D1 Y0, D2 Y0, and then when I differentiate dx3, I also get this. So here I get just B1. That's exactly my matrix B. Let's collect the terms of order X3. They come from here. So I have D1 B1, D2 B1, and then if I differentiate this in terms of X3, right, I pick up exactly X3 multiplier, and I have B2. This unknown so far, B2. And plus terms of X3 squared, higher order terms, everything is smooth. B2 will be smooth as well. So that's gradient UH. So now what is, let me compute the metric that's immersed by this, gradient UH transpose gradient UH. Okay. So again, terms of order 0 in terms of expansion in X3, it will be B transpose B. Plus terms of order X3, I have a product of this and this in both ways. So twice, twice X3, symmetric part. So let's give this guy a name. Okay, so let this be B0 and this is B1. So I'll have B0 transpose B1, right? And then higher order terms. Of course, we remember that B transpose B was a G. That's an important information. G of X prime 0, the full 3 by 3 matrix G. These are all 3 by 3 matrix fields. Okay, so let me also compute, because under my integral signs in the energy, I have gradient UH, G inverse 1/2. So let's see what I can say about G inverse 1/2. So G of X prime X3 inverse 1/2. Let's denote it by A X prime X3 inverse. Okay, so A is the square root of G, right? A square, a symmetric matrix. So A is the square root, just G 1/2. Okay, that's my notation. So okay, I don't have time to do that, but that's actually an easy calculation, right? So just I want to do the Taylor expansion of this guy around X3 being 0. Okay, so this is A of X prime 0, and then you have to just compute what's the derivative of the inverse of the matrix. So sorry, inverse, right? The same function of X3 equals 0, inverse. And then it turns out to be minus X3, A inverse, D3A, A inverse, everything at X prime 0, plus O of X3 squared. It's just a form. Very good. So now I want to understand what's my integrand. That is gradient. Maybe I'll do it. I'll do it here. So gradient UH, right? I want to look at gradient UH, G inverse 1/2, right? That's what's sitting under the sign of integral under W at all X prime X3. Right? So now I make this trick because my W is frame invariant, so it's invariant with respect to multiplication by rotations. Okay? Actually, I'm going to use the polar decomposition theorem, and this will be R times the square root of this guy transpose itself. Okay? So G inverse 1/2, that's my notation, that's just A inverse, times gradient UH transpose gradient UH times this guy, A inverse. So that is R times, okay, square, so I can write square root of a matrix. And now what do I have here? So this is all computed, of course, at X prime X3. So now I'm going to multiply. I computed gradient UH transpose gradient UH. And I have to, so I have this formula. From the left, I multiply by this formula. And also from the right, I multiply by this formula. Right? I have this guy from the left A inverse, from the right A inverse. So that's what I'm going to do. This formula from the left by this multiplication, and from the right also by this. And let's gather terms. Okay, so first of all, terms of order 0 in X3, I will have A inverse times this term, which is G, times A inverse. So that's identity, because A inverse is exactly, A is exactly the square root of G. Identity, it's a three-dimensional identity, plus. How do I get terms of order X3? Okay, so first and foremost, I have this guy, which has 2x3 something. So from the left by A inverse, from the right by A inverse. Okay, it's 2x3, A inverse, B0 transpose B1 symmetric part. I write it like this. From the right, A inverse. Okay. Now I have to gather terms when X3 comes from here. Okay. So I will have this times B0 times B transpose B, which is G, and times A inverse from the right, twice symmetric part of it. because everything is symmetric. Okay, so there is this minus sign here, so minus 2x3. Symmetric part of, okay, so I have A inverse D3A, A inverse, but then it's multiplied by G, which is A squared. So that's just A. And times A inverse. So of course it's nothing, but I prefer to still write A inverse here. Symmetric part of it. Plus of x3 squared. And the square root continues. So that is rotation, square root, and now I have identity, 3 identity, plus 2x3, and I want to put this A inverse here and A inverse here outside. So I have A inverse. From here, I have B0 transpose B1. Symmetric part of it, of course. Minus D3AA, symmetric part of it. And A inverse outside. Everything at x prime 0 plus of x3 squared. So this looks very good. Now observe that that is exactly 1/2 D3G. Okay? X prime x3, right? Because G, you remember, is A squared. So D3G will be twice, okay? D3G is twice, I mean, it is D3A, A plus A, D3A, okay? Which is exactly this. So I have the symmetric part of it, just easy calculation. On the other hand, what can I say about this thing? How does this look like? So B0 was D1 Y0, D2 Y0, B1 transpose, and B1, I'm just gathering terms, then copying the formula, is D1 B1, D2 B1, B2. Okay? So the tangential minor is multiplying this transpose by this, which is exactly gradient Y0 transpose gradient B1. Okay? Then what I see here is scalar product of B1 with D1 B1. B1 is a unit normal. No, it's not unit. So it doesn't matter. So here it's something defined. Okay, so this is, if it was unit normal, it would be 0. So here you have B times gradient B1. B1 times gradient B1. Okay, B1 transpose gradient B1. Doesn't matter. And what I have here comes from B2, which I don't know yet what it is. Okay, so I can define B2 basically to get whatever I want because the other matrix is invertible. And now observe what happened, that this minus the 2 by 2 part of this is 0. Because Y0 was the minimizer to 0 of I2. And what I see on the tangential component is exactly what I have here. This is a little g, by the way, right? So on the tangential component, this minus this together they are equal to 0. And now the catch is that you can define B2. Again, this matrix is invertible, being what? That's my B, and I know that B transpose B, is G. G, of course, is non-singular, so B is also non-singular. So I can always define B2 here, this last column, right? I can write a formula for it, so that not just the tangential minor, but the entire 3 by 3 difference of those matrices is 0. Okay, so define B so that, okay, this whole thing here, let's call it star, equals to 0. I can do that. So this already is 0, but my choice of y0, an assumption that such y0, which minimizes I2 to 0, exists. So in conclusion, this is R root identity 3 just of O of x3 squared. But that is R times identity 3 plus O of x3 squared, whatever that is, right? The square root of that identity is like, 1 plus something. If you want, if it were just numbers, scalars, the Taylor expansion would be 1 plus 1/2. So like this, the same matrix context. Okay? So what's the EH of my EH of that particular UH? I remind you, is 1 over H integral on omega H. W of gradient UH G inverse 1/2, right? That's our definition. And I've calculated, here I calculated gradient UH G inverse 1/2 comes to this. So that's 1 over H integral omega H. W on rotation, okay, times identity plus something of order x3 squared. Of course, W is frame invariant, so this rotation doesn't matter. Okay. Further, W, you remember, close to identity, I mean, close to anybody in SO3 acts quadratically. Okay. So really, this is quadratic on this, but that's already quadratic. That's why I get the particle. So this is 1 over H integral omega H, O of H3 to power 4 dx. Okay, so this is like CH4. Because X3 goes from minus H half to H half, so it's a order H. So, of course, at this point, I want to understand what's the gamma limit, right? So we are exactly in the situation as 2 classes ago. I know, I mean, we are in a better situation. We are not really assuming H. No, we know that the next energy level is H to power 4. So now I want to understand what happens when I have a sequence of deformations that scale in that particular way. What are the compactness properties and what's the gamma limit? But before we do that, let me now formulate a general theorem. In its spirit, similar to what we discussed here. Okay, so in spirit, similar to that particular statement here, which says that from H squared, automatically you jump to H4, and that is detectable by checking properties of the Riemann curvature tensor of my pre-strained metric, namely those 3 curvatures have to vanish equivalently. And that's also equivalent to existence of this Y0, which produces B0, okay, as such that I have certain formulas holding. The following theorem, the following statements are equivalent for all n greater or equal than 1. 1. Infimum of the H scales like CH 2 times n plus 1. So when n is 1, this is h to the power 4. I already know that the scaling of h to the power 4, which is equivalent to scaling faster than h squared, is equivalent to the vanishing of those three curvatures. So now I'm going to tell you what other even powers of h scalings are equivalent to. And in fact, it turns out that only such even powers of h are viable, are possible. So that's the first. So the following statements are equivalent. Okay, so the first statement is just that.
One quick question. So in the last line, can you explain again how the ID does not contribute? Yeah.
Because W at identity was 0.
So that has to do with the mid-plane.
No, this was our assumption. So you can think W is like distance squared from SO3, then it's obvious, right? So in general, this was the condition that the elastic energy of identity does not, in fact, of any rotation, does not cost anything. So W at identity is always 0, and then it departs from identity, in fact, from every rotation quadratically. Yeah? So that's the first condition. The second condition, there exists smooth fields y0 and b k's. Those k's go from 1 to n plus 1, that's b, from omega bar to R3, from my mid plate to R3, okay? Such that calling, I'm going to build my frames, higher order frames. So first I have B0. B0 is my old friend. B0 is D1 Y0, D2 Y0, and then B1. Okay, so n is greater or equal than 1. So I have at least one, I have B1, but I also have B2, but I may have more if n is larger. Okay, so this is B0, and then I have BKs, which is B1, D1 BK, D2 BK, and BK plus 1, and those BKs I have from k equal 1 to n. So those BKs are like the B1 here, which was D1 B1, this was my Coursera vector, D2 B2, and then D2 B1, and then I had this B2, which I, like another second generation of the Coursera vector, right? B2, which I have defined so that I was able to pass to H4. Here I have n plus 1 BKs, and for each of them, I generated this frame, which is D1 BK, D2 BK, and then the next one. Okay? There exist smooth fields such that calling B0 this and BK this, we have the expansion, so this is a sum from k equals 0 to n, x3 to power k divided by k factorial bk. Okay, so before I had b ingredient UH. I had b0 plus x3 b1. Now I will have x3 squared divided by 2 b2 and so on, and I go all the way up to bk. This thing is a square root of g up to appropriate order, which is n+1 order. So this thing transpose itself equals G of x prime x3, right? So all those BKs, all those vectors live just on omega, so they are functions of x prime, but here I have x3 also exhibited, okay? So this is G of x prime x3 plus O of h to n+1 on omega h. So what was happening before, when I had just one of them, if n is 1, right, then I have b0 plus x3 b1, or rather, let's think that n is 0, okay, and I'm formulating it because we know what happens at n equals 0, but let's draw this parallel. So when n is 0, this is just b0, and I know that b0 transpose b0, that's what's written here. This is exactly G at x prime 0. So it differs from G of x prime x3 by just 1 over of h. This is why I have here this h to power 1. Now I have h to power n+1. Of course, when n is 0, this is just trivial, right? So b0 transpose b0 is just G of x prime 0. So the difference to any x3, of course, is h, so it's trivial. But here I have a polynomial in x3, and I say that this is a possibly non-symmetric square root precisely of my G up to that order which appears in the energy. And I say, this is very interesting, in my opinion, that 1 is equivalent to 2. It's not just one direction, right? So automatically, if I have this, there exists this sequence of family of frames which allow me for this decomposition, and this is equivalent to this scaling of the energy. Condition 3, again, equivalent, 1 equivalent to 2, equivalent to 3, R1, 2, okay, ij at x prime 0 equal to 0. So this is for every ij from 1 to 3, right? These are the three r's that had to disappear already when n is 1. When n is 1 or anything more than 1, then of course they also have to disappear. But also, okay, so n, the 3k are, so now I look at other r's, not just tangential on the first two terms, first two coordinates. I3, J3 at x prime 0, that is 0 for every ij from 1 to 3, okay? I mean, from 1 to 2, really, because I have 3 here, so it doesn't matter. Okay. For every k, that's between 0 and n minus 2. Okay, so that's very interesting. That's the way of detecting the scaling of energy of order h to power 4 or h to power 6, but only those powers are possible. Okay? You have to look at the vanishing of the Riemann curvature tensor on the midplate up to certain order, which order n minus 2 turns out. Okay, so when n is 1, this means this condition is void, and I only get this condition. When n is 1, this means this is h to the power 4 scaling. That's exactly what we had before. Yeah. Moreover, I continue the theorem. Moreover, we have Okay, so all those curvatures vanish. So the first one that does not vanish, so k equal n minus 1, put here, is exactly the term which makes, it's exactly the difference of this and this at this order which is prescribed here. Okay, so I have the following formula twice. D3, so k is now n minus 1, are I3, J3 at x prime 0. So I view it as a matrix in Ij from 1 to 2. Okay, so I just put, I arrange, I have R1, 3, 1, 3, 1, 3, 2, 3, 1, 3, 2, 3. Of course, they are the sign, 2, 3, 1, 3, and 2, 3, 2, 3. Okay, so this will be like, this will be a matrix. I put it in the form of a 2 by 2 matrix. This thing equals, I can compute twice, gradient y0 transpose gradient bn plus 1, symmetric part of it, plus the sum from k equal 1 to n plus 1 choose k, gradient bk transpose, gradient b n plus 1 minus k, symmetric part, minus d3 n plus 1 g x prime 0, 2 by 2. Right, you see? If I want to, so condition 2 tells me that this equals to this modulo this thing. So let's, if I write a Taylor expansion of G in terms of x3, okay? I claim here that all the terms disappear up to x3 to power n plus 1, which is carried by the derivative, n plus 1 derivative in the direction of x3 of my G. Okay? And the difference when I gather the terms of order, exactly this leading order, x3 to power n plus 1, from this, I will get this. I will also get a term from, because you remember in B0, I have y0, okay? So if I take here just B0, then I have to, of course, multiply by the highest order of them, which is coming from Bn plus 1. So that's why we'll have gradient little Bn plus 1. And then the middle intermediate fields are here, and that's the difference. So I claim that the highest order, the fact that this is of this order, okay, in the difference, this order, the coefficient at h to n plus 1, it's exactly the first non-zero component of the Riemann curvature tensor when I'm looking at its derivatives. Okay? So all the previous ones are 0. This one, the next one at n minus 1, it's exactly given like that.
Yeah, excuse me. Yeah, I want to check if I'm understanding correctly. So the theorem on the left, it says that if our I2 is 0, then the incompatibility is resolved, but with the normal becoming B0. The theorem on the
Sorry, say it again.
Okay. So the theorem on the left, yeah.
Yes.
So it says if I2 is 0, then our incompatibility is resolved, meaning our Riemann curvatures, they become 0, but with the normal becoming B0.
Yes.
Yeah, and then that B0 sort of in the when the energy scale is higher than h squared, then that B0 sort of defines the energy.
It's always there. That's right.
Okay.
Right. So here I just state. So maybe let's look at this first. So infimum going faster than h squared means effectively that infimum is h to power 4, that's it. And I say that this is equivalent to having, there is no end, equivalent to those three guys being 0. This is like condition 3. Okay? And here I observe that in that situation, I can define uniquely a smooth y0 and a smooth b1, which are such that they make my I2 0. This is I2. So I2 is computed out of y0, and b1 is computed out of this formula, and this I2 is 0. Okay? So I say that the same situation is happening, the same precise description you can carry out in higher energetical orders. So you see, here I say infimum is like h to 2 times something that's equivalent to having not just this equals 0, but the whole curvature equals 0 up to a certain order.
It's a grade of y0 plus b. Is it b1 there? And
this is, no, this is not, that's not the b, that's, sorry. So that's just a rotation.
okay, yeah. Okay, yeah.
Right, translation, sorry, rotation and translation. Okay, maybe that was confusing. You see, I wrote that first and then I defined the second. Yeah? No, this just says that kernel of I2 consists just of a single smooth isometry, of course, modulo rigid motions, right? Everything is modulo rigid motions. So this has nothing to do with the Cosera vector. That's just the rotation and translation. Yeah. Thank you, very good.
Can I just ask one maybe related question? Is so in I2 or essentially in the Riemann curvature tensor set to 0 has both the Kodacki condition and the Gauss equation built into it, right? Yeah. You have the Kodacki condition as well as the Gauss equation is somehow built into it. But when you come here for that star term, you don't have the gradient in B2 vector. Somehow it's built into it. I'm not seeing it.
I'm sorry, I didn't follow at all. You are asking this calculation here?
Yeah, for that star term. So B2.
For the third term?
No, you have that star, right? The star.
Star term, yes, yeah. Exactly.
So you have B2, which is there, B2 vector, which is there.
Not yet defined. So here I only have y0 and b1.
Yeah, x3 times capital B1, right? Has the B2 vector in it.
Yes, I say B2 will be defined later, to be defined. That is my ansatz that I make. UH is y0, okay, which I know, B1, which I know, and I say I have to, at the level of x3 squared, add something else. I don't know what it is yet, okay? And here I'm telling you that this is the fact that if y0 and b1 satisfy this condition, this means that there exists a b2. I can define a b2, there is a formula which I'm not writing, okay, don't have time. I can write b2 such that this whole thing, star, will be 0. Not just the 2 by 2 component of star.
Question was, there is gradient of small b1 in that matrix, right? But
yes,
there is
gradient of b1 here.
Yeah, but you don't have gradient of b times.
That's right, I don't have gradient of b2 here.
Yeah.
This is why I can find b2 basically by inverting that matrix so that I put here, okay, so that, you see, this is already, so in the star, how does the star look like? Okay, so star is this minus this. So the 2 by 2 minor of star is 0. And then I have outside is, this is defined minus whatever is the last row of this guy, okay? And this is something that I am free to choose, okay, minus the last row of this. And then I say, I am able to, so, and after symmetrization, you want this to be 0. So you have to define this such that this minus the last column, after symmetrization equals, plus this equals to 0. You have an equation, so you can do that. Okay?
constraint is also coming from I2 equals 0, is it? So, so that condition that you just impose at the end is also coming from I2 set to 0.
The I2 set to 0 only tells you that in star, the 2 by 2 minor is 0. That's equivalent. That's exactly. So we discovered that the 2 by 2 minor of star is this minus 2 by 2 minor of this. That's exactly written here. You see, gradient Y transpose grade B, symmetric part of it, minus 1/2 D3G. That's exactly 2 by 2. Okay, thank you.
Excuse me, I also have a question. One more question. So, to me, the condition of the Riemann curvature being 0, to me, the condition of the Riemann curvature being 0 was the condition to have an isometry of the in-plane metric. But this would lead to a pure bending.
But that's not the full Riemann tensor, right? And so for a 3-dimensional metric, I have 6 Riemann curvatures. So, I mean, okay, in general, I have many more, but I have independent 6 Ricci curvatures. Here I am putting to 0 just 3 particular ones, and moreover, only on the midplane.
Yes, yes. So, okay. So to me, this was a condition to have to be able to cancel the in-plane strain or the deviation to the metric. To have something. Okay, but then I thought we will in pure bending. I mean, bending some bending energy would remain. No, but the bending energy is 0 now. Also, it's assumed we assume that we assume that there is no bending energy. That's the first line. Okay. Sorry.
Okay, so this condition is equivalent to having this.
Okay. So
not infimum, not the full infimum equals 0. No, no, no. This cannot happen unless everything is 0.
Yes. Okay. I understand.
Okay, so let me speed up because I have to tell you what happens next. Okay. So, so I'm going to skip over, a lot of interesting things, but so we have this result, which is valid at any even power. Right? So you had questions about that theorem. This is like higher infinitely many statements of that type, in a sense. Okay? So what's the compactness and what's the gamma limit? So you remember for the theorem at the level of I2, the compactness was that the rescaled UHs converge to that Y, okay? Which was one deformation of regularity W22, and that was the argument of the gamma limit, which was I2. So now I want to develop a compactness statement of this type at higher order energies. The theorem, if EH of UH less or equal than CH2 n plus 1, so I always fix here, right? I fix a particular n greater or equal than 1. And assume that you have a sequence of deformations, which scales like that. So this can be infimizers or not. That's the assumed scaling. Then I claim there exists a sequence of rigid motions, a rotation in SO3, and a translation in R3, okay, such that condition 1, I will have to look at the displacement with respect to Y0 and its normal displacement related to the sequence of BHs, of BKs that I have defined. So VH is defined, VH of X prime, is defined as 1 over h to the power n Now I take the average. This is the, so I have a further 1 over h here, from minus h half to h half. This RH, UH at x prime, x3, minus CH. Okay. I continue under the integral, minus y0 of x prime, plus the sum from k equal 1 to n, x3 to k, divided by k factorial, dk of x prime, dx3. This is my definition of VH. So I'm checking, I'm just centering my UHs. So modulo rigid motion, that's just a UH, right? I average it, and I subtract, so I mean dx3, you can have dx3 already here, right? That's, no, sorry, this is x3 here. So you are subtracting, this is like your recovery sequence. You start from that uniquely defined smooth immersion y0, which makes I2 equal 0. And then you add the expansion in terms of BKs, which are given here, right? Because you know their existence is guaranteed by the infimum of the energy being of this order. And the statement is that, okay, modulo some rotation translation, this displacement, which are just defined, converges strongly in W12 to V. And this V is of regularity W to 2, and it's an first order infinitesimal isometry. So this V belongs to the space curly V sub y0, which is defined as collection of V's which are in W to 2 from omega to R3. So again, this limiting displacement is of higher regularity than the original one. And moreover, it must satisfy gradient y0 transpose gradient V. The symmetric part of it is 0 in omega. You should think about this capital V like as of an out-of-plane displacement. You see, if your y0, okay, if y0 was just, say, identity, two-dimensional identity, if it was flat, okay, then this would say that the symmetric part of the gradient V is 0. But V is a three-dimensional field. Okay, so V goes from 2 dimensions, from two-dimensional midplate to R3. So V is like V1, V2, V3. What does it mean that its symmetric gradient equals 0? It means that V1, V2, I'm sorry, that V1, V2 must give you a rigid motion, because we already learned in the first class, Lewicka theorem, if the symmetric gradient is 0, then it means the gradient is constant, skew-symmetric. And you will have an unconstrained V3 out-of-plane component. So this, for this condition we call the first order infinitesimal isometry condition, is a replacement. Okay, so this is a space of first order infinitesimal isometries. You should think in this context is the replacement of just the space of out-of-plane displacements, albeit regularity W22. Okay, so if I have that, then modulo rigid motions, the UH departs from this expansion, okay, given by uniquely defined frames that give you the square root of G at appropriate order, by something which accumulates at a higher order regular W22 first order infinitesimal example. 2 scaled strains. So if I look at 1 over h gradient y0 transpose gradient vh, symmetric part, right? So the gradient vh converges to gradient v, and gradient v has this property that it's together with gradient y0 transpose symmetric part is 0. So this without 1 over h converges to 0. So now I scale it by 1 over h, and it turns out it also has a limit. Okay, so this actually converges weakly in L2 from omega to R2 by 2. Okay, converges only weakly to some limit. I call it as limiting strain. And this S belongs to the space curly SY0, the space of limiting strains. And here there is no new information. Here there was a new information, right? That this limiting V was like that. Here I define SY0, the space of limiting strains, as just the limits as n goes to infinity in L2 of gradient Y0 transpose, gradient Wn, symmetric part, and where this Wn are in W12 from omega to again R3. So you should think of those, of the space of the limiting strains as symmetric gradients of in-plane displacements, if you are in the classical elasticity context, okay? But here, these are not necessarily, so given Y0, which of course depends on, on the G, right, as we discussed before, this Y0 uniquely defines a space of limiting strains. So you have to compute it. So example, right, I don't have 5 more minutes and I need to still say something, okay? So just example, if the Gaussian curve, if say Y0 is identity, then from this it follows that SY0, indeed, these are just symmetric gradients, the space of symmetric. So these are such fields whose curl is 0. That is symmetric gradients. Okay, so let me write symmetric gradients down. But another example, if the Gaussian curvature of gradient Y0 transpose gradient Y0 is strictly positive, okay, so if Y0 is convex, then in fact, SY0 consists of all, not just symmetric gradients, of all L2 symmetric fields. So of all, this equals L2 from omega to R 2 by 2 symmetric. Okay, so it can be small or it can be very large, it can be everything, the space, depending on what is your Y0. And the statement is that elements of V, of curly V, and elements of curly S, those are the arguments in the gamma limit. So that's the compactness theorem, and now we want to compute the gamma limit. So just very quickly, theorem. So 1 over h to power. So assume 3 is 3 here, big 3. So this is big 1, big 2, big 3. Right? So that I know. So assume 3 at n equal to 2. That is, I want, n equal to 1. So this means just the 3, i.e. R1, 2, ij equals 0 in x prime 0. on omega. Okay, that's our condition corresponding to h to power 4, scaling of the energy. Now I tell you what's the gamma limit. Then 1 over h to power 4 pH, right? So then I know that the infimum is of the order h to power 4. Gamma converges to I4, where I tell you now what it is. So I4 is defined on V and on S. Okay, so defined for V, which belongs to Vy0, and S, which belongs to Sy0. This is the domain of the definiteness of I4. And, okay, I don't have time. There are three terms. Term 1, explicitly, of course, I have all the formulas. You can check. I will send my paper to everybody, okay? So there will be stretching, whatever that is. There will be bending, whatever that is. And there is a third term, curvature term. So the stretching and bending are computed out of V and S, and of course they are appropriately relative to the metric and right to everything. And what's the third new term? It's very interesting. It is, okay, it has a certain prefactor, 1 over 1,440. And then you will have the integral on omega, exactly the length of the matrix, 2 by 2 matrix, which carries the 3 possibly non-zero Riemann curvatures. R1313, R1323, R1323, R2323. Okay, at x prime 0 square. And again, this is in fact that Q2, which is computed out of W, that's this quadratic form, which I am applying on this 2 by 2 matrix. Precisely to the dot. This is not just equivalent. That's exactly the third term that you get. Okay? The 3, it carries the 3 curvatures, which were missing from the full curvature being 0. So this is what happens at the level of I4. What happens at energy when n is strictly bigger than 1? That's the next statement. Theorem. Assume condition 3, right? Condition 3 in the big theorem at some n strictly bigger than 1. Okay, so assume that I know that this condition is equivalent to infimum of the energy scaling like h to power 6 or h to power 8, I don't know, any of them. Then okay, sorry, I have to rush. This is the last thing. Then 1 over h to power 2 n plus 1 EH. Right? That's what I want. Gamma converges to I to n plus 1. And I will tell you what it is. So I to n plus 1 is defined only on V. So here V is in the space of first order infinitesimal isometries with respect to Y0. So these are like your out of plane displacements, but morally speaking, everything was trivial, there was no metric, then modulo rigid, infinitesimal rigid motions, this would be out of plane displacements. Now you don't have out of the surface displacements. You have exactly the member of that space. And what is it? So you have something that's like bending, so 1/24 integral on omega, and you have Q2, and okay, so okay, let me write, I don't have time to discuss. So the covariant derivatives di dj of that V in the direction of B1. This is the principal Cosera vector. But this is relative, so there is just a constant alpha n here, all given precisely. I don't have time to tell you what that constant is, okay, but it's explicitly precisely computed. And here I have D3 n minus 1. So I will see that the first non-zero component of this non-vanishing component of the curvatures. I have Ri3, J3. So this is of course at x prime 0, and this is Ij going from 1 to 2, and you are applying Q2 on this. So this is the first term. Very interesting. So you have like a bending term, sort of bending, but now it's relative to the preferred bending that's computed out of the metric via this formula. So those Riemann curvatures give you exactly what you have here. So this is the first term, plus, now I have two more terms, which are sort of in the spirit of what I had here. You see, I had stretching, bending, and now I have curvature. So I also have curvature there. But, okay, so two terms, beta n and gamma n. Again, these are scalars which are given explicitly. And here I will have the norms, the integral on omega Q2. Here I have to look at the projection on the S, on the strain space, finite strain space, Sy0, of exactly this thing, D3 n minus 1, Ri3, J3, x prime 0. You have to take this matrix, so Ij from 1 to 2. Basically, you have to take the L2 norm squared of this, but it carries different coefficients in the finite strain space and in its orthogonal complement. So there is another coefficient here, Q2, at the projection on Sy0 orthogonal, D3 n minus 1, the same curvature, I3, J3, x prime 0, Ij from 1 to 2, dx prime. Okay, so that's the gamma limit. So the photo is waiting. My time is completely over. So still just 1 minute. Just to finish this completely. You may ask yourself whether all those powers of H are viable. So indeed they are, because example, if you take G of x prime x3 equals exponential, and so let's see, so what do I want? Let me put x3 to power n, exactly, identity 3. So there's a conformal metric, the conformal factor being just a polynomial in x3. Okay, it turns out that for this metric, exactly the condition 3 works with, I guess, n minus 1. Yes. So for this metric, infimum of EH, is like ch to power 2n, less or equal, but it's greater or equal than a small c, still positive, h to power 2n. So I'm just saying that this infinite hierarchy of limiting, GABA limiting theories, all of them are viable. So if you want the scaling of your energy to be exactly like h to power 2n, okay? In particular, you can take a metric like this. And that's not just upper bound, but also has a lower bound. And then the gamma limit, it is as I described. So there are, of course, many interesting questions, many ramifications of those theories. We haven't covered the Monge-Ampere constraint, theories which are related to the so-called weak prestrain. So in what I discussed, my prestrain was just one given fixed metric G, right, with large Riemannian curvatures on the referential configuration, but one could think of G being, say, a small perturbation of an immersible metric, small perturbation of identity, and then you will have that perturbation, you know, has a certain order in H and certain leading term, and it turns out then the Monge-Ampere constraint, like in the linearized Kirchhoff in classical elasticity, where I look at displacements such that determinant Hessian, whose determinant Hessian is 0, so this is a constraint on the Gaussian curvature only, basically shows up. So you can also have a hierarchy of theories like this for the weak prestrain. But I hope that was a good beginning, good start for you to understand, to get accustomed with this kind of analysis. In my opinion, is also mathematically very complete and beautiful. And I stop here. Thank you. Puzzled. You look puzzled.
I have a very maybe naive question. So in the expression that you have for I4, so if you, yeah, so is it useful to, or is it right or absolutely wrong to think of the terms stretching and bending as essentially contributions coming from the fact that you have vertical displacement and that couples to the inclined strain, and that's what's contributing to the curvature? Yeah.
What's contributing to the curvature?
Yeah.
No, the curvature is exactly, I'm not sure if I understand the question. Curvature is exactly this. Stretching, bending are given in terms of, you know, V and S. I could write just you know, this one. So for example, okay, the stretching, just again, you have some integral on omega, and basically here you have your S, the S that's here, plus, okay, there is 1/2 gradient V, transpose gradient V. And then you have 1/24 gradient B0, transpose gradient B0, and now interesting, minus 1/48 D33 G, X prime 0, 2x2 component, okay, this guy squared. So that's exactly stretching, understood, you know, appropriately with respect to those limiting objects. So you are checking how far away you are from V, but this is like taking the Taylor expansion. So because I am at the energetical order h to power 4, I'm taking the second derivative of G at x prime equals 0, okay? I don't have time. I mean, it turns out to be this. And bending is also something else. You have stretching and bending, and this is the curvature, all the curvatures which are non-zero at this energetical level. Okay, and I found it interesting when I mean, this theorem is due to me, when I derived this, that, you know, I was not sure what to expect in the gamma limit, and I was amazed that to the dot, this is not just, you know, equivalent or something. That's exactly the the energy density, the same energy density that's calculated out of W, okay, you know what it is, and it measures, here it measures the second order deviation from the metric as it should, here it measures the deviation from the second fundamental form of the appropriate, you know, with respect to this expansion of V and S. And here you exactly measure the first non-zero at this so I don't know, you don't have orders here because you have all Riemann curvature components, but this is the first non-vanishing component to the dot. You have this term, this non-zero term. I don't know if it answered your question, but
this term that is there in the stretching, the grad B 0 transpose grad B 0 is actually what I was asking about.
Yeah, I mean, these are explicitly given. I don't have time to find formulas. No. It is what it is, exactly. So this, what you see, my original EH, we checked, right? It was like first of the second class. That EH, what makes EH non-zero? The curvature, okay? What makes the gamma limit reduced, dimensionally reduced EH at this energy level non-zero? Of course, if S is 0, V is 0, this is, okay, I don't know, maybe this is 0. You can always put this and this to 0 somehow. I mean, not always. Okay, I'm getting ahead of myself. But the bulk term, which is always here, what makes this non-zero is again the curvature, but not all the curvatures. You see, you know, you have this infinite hierarchy, and in that hierarchy, you see which portions of the curvature are driving that energy level. Okay, exactly this one here. Okay, and in higher orders, that's what see here. That's exactly D3, okay, and -1, the next one, which is not 0, right, from condition 3. But it's also interesting, you know, I don't have time to comment on that, but here you have the split between the finite strain space SY0 and its orthogonal complement. So you have to decompose these curvatures. They come with different, so those be ends. And also, you know, sometimes it can be, both of them are never 0. But sometimes one of them can be 0, depending again on the parity of n. So there is more discussion here, but I will leave it for next time. Yes.
So I have a question on the example, which is which I like because it's very simple. So I used to think about this. I mean, this G bar and B bar that we saw with Effie coming from from moments of the metric. I mean, G bar is the metric at the center line or the average metric, and then B bar is coming from some moment of the metric. Oh, yes, all the derivative, but then if you have powers like this, I think it's easier to think about it in terms of moment because the D3 will be 0. I mean,
yes, so this is the example of a metric which satisfies condition, exactly this condition, up to n-1.
Yeah, because all the first derivatives are 0. Yes.
Up to n-1. I mean, the curvatures, right? You have to compute what are the curvatures. It's not just the metric.
Yes.
So not derivatives of the metric.
Yes. So one question is, okay, so this is for n odd or even. This is for the example. And there is no assumption on the parity of n.
Any n, yes, any n.
So I would say that, okay, if I think about it, I mean, intuitively, it seems that for n even, then the sheet will be flat. There will just be in plane strain. And for n odd, it may want to curve still at finite.